So today we're going to be finding limits analytically. There are three ways to find limits. We kind of dealt with finding limits graphically, just seeing the picture. Numerically, using a calculator, kind of plugging in inputs close to where we're looking at. Today is analytically. And we'll have today and Monday will be two different lessons on finding limits analytically. Okay? And we're going to get back to this example of how to find the limit as x approaches 1 of this. But before we go there, let's go somewhere else. It's very important to know that most functions that we deal with are continuous functions that have limits everywhere. Let's take 3x minus 2. I'm asking you what is the limit as x approaches 5. If I were to sketch 3x minus 2, you'd have a y-intercept, a slope. It would look something like this. Right? There are limits everywhere on that graph. There are no holes, there are no asymptotes. It's a piece of cake. If I want to find the limit, sorry about that. As x approaches 5 of 3x minus 2, all I need to do is find the location of the point where the input's 5. So all you have to do is plug in 5 into the function to see what the function value is. "13, I will be approaching 13 to the left and 13 to the right, and turns out my function value is 13. Piece of cake. Limit as x approaches pi of sine. Sine oscillates, it goes up and down, up to 1, down to -1, keeps going forever. It is continuous everywhere. There are no holes, there are no jumps, there's no asymptotes. If I wanted to find the limit as x approaches pi of the sine of x, I just need to find out what the sine of pi is. Sine of pi is 0. If I look at pi, the output is 0. I'd be approaching 0 from the left and from the right. So the limit is the same as the function value. We talked about that last class with just graphically, how we can have limits not just at points with holes on them. It could be anywhere. Are we cool with this? Good. Same for tangent, same for x squared. This is 9, this is whatever this is. Okay. So if I give you an equation like this, f of x is equal to x squared minus 1 over x minus 1, and I ask you to find the limit as x approaches 1 of this function, the first thing you should do is say, hey, does the function value exist at 1? And you will try to figure out what that value is. Well, let's do it with x squared minus 1 over x minus 1. I get 1 squared minus 1 over 1 minus 1. That's 0 over 0. That is undefined. Cannot divide by 0. You can't even divide 0 by 0. Indeterminate. So no, the function value doesn't exist for this situation. If I had my calculator, I would probably type in 0.9999 and 1.0001 and figure out what those function values are, and that would tell me what I'm approaching. I can't do that here because I don't have a calculator. So this is cool if you have one. If you don't, I'm not going to do this by hand. It would take me too long. Instead, let's see what we can do. Let's go ahead and say not without a calculator. F of x is an interesting function. It actually can be simplified. X squared minus 1 is a difference of squares. it can be factored to be x plus 1 times x minus 1. Over x minus 1. And before I even continue with the simplification, let's look at this. Let's just say we do have a calculator. Let's make sure that the limit exists, or else we're going to be wasting our time. Let's look at the graph of x squared minus 1 divided by x minus 1. Actually looks like a linear function. However, if I try to trace and go over to my point 1 when x is 1, I notice there are no y values. But we are approaching at 1 some value. We could probably guess what it is. Okay? But what is not shown is an open circle or a hole. If we had our calculator, it's easy to find that hole. If we don't, this is what we're going to do. We're going to simplify our function. And we notice that this x minus 1 and this x minus 1 cancel, eliminating that problem that prevents me from plugging 1 into my function and getting an actual answer. So what's created is a simplified function. We'll call it a g of x. It doesn't matter what it's called. But g of x is a simplified f of x. And let's compare these two functions. Maybe let's look at a little bit of a table for different x values. Let's say -1, 0, 1, and 2. For my f of x, which is my x squared minus 1 over x minus 1, and my simplified g of x, which is x plus 1. Okay? Let's start with -1. I plug in -1 into f of x. -1 squared is 1, minus 1 is 0. -1 minus 1 is -2. That's 0. Sweet. I plug in -1 into g of x. I get -1 plus 1. That's 0. So this was -1 squared minus 1 over -1 minus 1. And this was just -1 plus 1. I go to 0. 0 minus 1, 0 minus 1, -1 over -1 is 1. 0 plus 1, 1. I plug in 1. I can't plug in 1 to this. We have an undefined value. We have an error. We have a hole. However, I can plug 1 into g of x. 1 plus 1 is 2. I can plug in 2. I get 4 minus 1 is 3. 2 minus 1 is 1. 3 divided by 1 is 3. I plug in 2. I get 3. Turns out, if I graph f of x, f of x will have this hole at above 1. That's f of x. But if I graph the simplified f of x, g of x will lie on top of f of x. It will mimic f of x everywhere, and it will fill in my hole. So if I want to know where the location of this undefined value is, I can just look straight to g of x, and I can say, oh, it's 2. And this is how we are going to find limits without the use of our calculator. So to kind of tie it all together, limits of functions that can be simplified. If f of x, or let's say if g of x is a simplified f of x, then the limit as x approaches c of f of x is going to be the same as the limit as x approaches c of g of x, and it's just going to be the function value g of c, because g will fill in all of the gaps and all of our missing information that we can't see if we just look at f. So just like I can see in my calculator, I'm approaching 1, 2 on my original function. Well, I can figure that out by simplifying f of x, creating g of x, and then just finding the limit as x approaches 1 of this g of x, plug in 1, I get 2. Does that make sense? Okay, that's what we're going to be doing. Now, what if a function can't be simplified? There are certain functions like 1 over x. And if I tried to find the limit as x approaches 0 of 1 over x, and I don't have my calculator, this function can't be simplified. I plug in 0, I get 1 over 0. That's undefined. Since it can't be simplified, that is telling me that the limit does not exist. Which you can see graphically if you looked at 1 over x. We have an asymptote. We are approaching negative infinity from the left or approaching positive infinity from the right. So functions that can't be simplified will have asymptotes. We won't have limits if we have an asymptote. The question is, how do we know if we can simplify our function or not? We kind of don't. We just need to try. You can't give up if you see a 0 over 0 after you plug in a value. You have to try to simplify the function to eliminate our problem, and then you will develop a new function that will mimic your original function and fill in holes where you can find where that missing function value is located. There's a bunch of techniques. This is pretty much review of algebra in calculus. Okay, this lesson and the next lesson. You're asked to find the limit as x approaches negative 3 of this function. The first thing you're going to do is try to plug in negative 3. In this situation, I plug in negative 3, and I'll let you catch up, write down the example. I'm going a little fast. First thing I would do is try to plug in negative 3. I get 9 plus negative 3 minus 6 divided by negative 3 plus 3. Well, we got 0 over 0, undefined. Now, that doesn't necessarily mean the limit doesn't exist. It could mean we have a situation like the last example where we have a graph with a hole. And if we have a graph with a hole, the limit does exist. It's where the hole is located. So we need to find the location of this hole. What we will have to do is try to simplify this function to create a new function. I know x squared plus x minus 6 can be factored to be x plus 3 times x minus 2. Keep x plus 3 underneath it. We know that this cancels, giving me a new function, which is similar to the other one. It's really the same, and it fills in all holes, x minus 2. To find the limit as x approaches negative 3 of this easy function, I plug in -3. And I get my limit is -5. Cool? Let's try another one. Now, when we're doing lots of examples in class, it might be good if you have a scratch piece of paper, just in case you make mistakes and you don't want to like cross out your mistakes on your real notes. So if you want to break out another sheet of scrap paper or just tear out something from the back, you can do that. Let's find the limit as x approaches -4 of this function, x squared minus 16 over x squared plus 6x plus 8. Once you get it, check your answers with a neighbor. It's -4, Mr. Glenn. Did you plug in -4?
I think so. I'm done.
Let's see. We can first try -4. I get 16 minus 16. And then I get 16 plus -24 plus 8. I do get 0 over 0.
Yep.
So you got to try to simplify to discover the missing location. Help each other out. If you need help, ask a neighbor. If you got it and your neighbor got it, see if you got the same thing.
Will the function always have a hole in it if you simplify it, or could it still be like?
Yes. What we're discovering is that at -4 we have a removable discontinuity or a hole. If we can't remove it, then it's an asymptote. And then we have a non-existent limit. Okay. All right. So back to algebra. Difference of squares. Now what we're doing is we're removing the problem. We're removing the hole. And this new function that we have left over is the same as the other one with the hole removed. Now if I asked you this same question and I changed this to -2 and you still can't simplify this -2, the answer would be does not exist because there'd be an asymptote at -2. I can't remove that problem. But there's a hole at -4 that can be removed, so we can discover after we plug in -4, we get -8 over -2, which is 4. Okay, let's do another one. You might be comfortable doing factoring when A is not 1. You'll have a problem like that on your homework. You might have to remind yourself. There's a trick I can show you if you want to learn the trick, but people forget tricks. So try this one, like hand tricks. People forget tricks. People don't forget truths. Yeah. All right, try to figure this one out. We're still factoring, so that's your hint. check with your neighbor, help your neighbor. This is a common problem seen on AP tests that deal with limits. It'll be just like this. All right, what's the trick, Miss Coffee? What do we have to do?
Take out the x cubed.
Yes.
Top and the bottom.
Factor out x cubed. And then what happens next?
They cancel.
They cancel. And what do you do?
Well, your x's are 0, so you just cancel out both of the ones with x terms, so it's just 8/12.
Exactly. You plug in 0 for x, because that's the limit that we're trying to find. This is my new function, just this piece. We're still trying to find the limit as x approaches 0. You plug in 0 into this new function that eliminates our problem. We get 8/12, which is 2/3. Excellent. Sometimes we'll have something like this. I'm trying to find the limit as h approaches 0 of the quantity of 4 plus h squared minus 16 divided by h. I'll call this f of x. If I try to find f of 0, I see I get 4 plus 0 squared minus 16/0. That'll be 0/0. So my function is undefined at 0. However, that might be the location of a hole rather than like an asymptote. If it's the location of a hole, the limit will exist there. We just need to figure out where that hole is located. So what we'll do is we'll try to distribute, and maybe that'll help us simplify our function and get rid of our problem child, which is this h. Distribute 4 plus h. Make sure we know that it's not 4 squared plus h squared. If I need to square 4 plus h, it's 4 plus h times itself. We get 16 plus 8h plus h squared minus 16, all divided by h. Now we notice something. We can eliminate the 16 and the minus 16, giving me 8h plus h squared over h. I could either divide everything by h, or I can factor out the h. The h's cancel. The question now is, what is the limit as h approaches 0 of 8 plus h? Plug in 0 for h, 8. Cool? Let's do another one like that, only I have x's and h's. Your answer will have x's. Don't worry. You will see on your homework x's and delta x's. Don't be scared. If this is delta x instead of h, it's okay. It's just another variable that you will eventually plug in 0 for. But for right now, let's just use h's. And check your answers with the neighbor. Sure we're okay with x plus h squared. X squared plus xh plus xh plus h squared, or x squared plus 2xh plus h squared. And we should get, in the end, the answer is 2x. X squareds cancel. You factor out an h. H's cancel. You plug in 0 for h. You get 2x. Okay? Sweet. Same deal here. Simple. Sometimes we have to multiply by the conjugate to eliminate our problem and to find where this function value is located. It's typically used when we see square roots. So I got limit as x approaches 0 of the square root of x plus 1 minus 1 over x. I attempt to find the function value at 0, but I immediately see I got root 1 minus 1 over 0. That's bad. Okay. Multiplying by the conjugate is useful, because if I have, say, a minus b, I can multiply that quantity by a plus b, and that gives me a squared minus b squared. The middle terms will cancel each other out. It'll have a positive AB and a negative AB, add them together, boom, gone. What I'm going to do is say that this root x plus 1 will be my A, and this 1 is my B. I'm going to multiply the top and the bottom of that fraction by the conjugate of that. So I will multiply by root x plus 1 plus 1. That will give me this a squared minus this b squared. Well, you square a square root, they're inverses of each other. You will just get rid of the square root, and you'll just have x plus 1. The b squared is 1, so a squared minus b squared. Now in the denominator, you might think, hey, let me just distribute that x, and I'll have x root x minus 1 plus x, but that's actually going to hurt you in the long run. So instead, we're just going to write it out without distributing. X times root x plus 1 plus 1. What happens is that the 1s will go away, and we'll leave ourselves with x over x times root x plus 1 plus 1. Those x's will cancel, and we can now find the limits because we get rid of that problem that prevents us from plugging in 0. We will find the limit as x approaches 0 of 1 over, lines are so tough, roots x plus 1 plus 1. I plug in 0 for x. I now have 1 over the square root of 1, which is 1, plus 1, which gives us 1/2. Turns out this equation will approach 1/2 as x is approaching 0. Okay, let's practice that again. Check your answers with neighbors. You got it? Just simplify that. Good. Okay. So you got to make sure you multiply 3 and 3.
Oh.
Give you 9, negative 9. Okay, now if this is minus, this is plus. A minus b times a plus b is a squared minus b squared. So you got that minus 9. Good until the end.
Oh, yeah, what?
So what did you plug in for x?
4.
4, okay. So you get 1 over the square root of 9 plus 3. What's the square root of 9?
3.
What's 3 plus 3? Good. All right. Perfect. Awesome. Awesome job. How we do?
I got it, I think.
Good.
After this,
Yep.
I'm flying down here.
Okay. So once you're multiplying by the conjugate, you gotta have this squared, which you have, minus the b squared. So minus 9. Then you'll simplify that 5 minus 9. You'll go from there. All right. Okay, should get 1/6. Now the key, and for those of you, if you're struggling with this first part, so try not to skip things. Remember, if we have, x plus 5 times x minus 5, you'll get x squared plus negative 5x plus positive 5x minus 25, or plus negative 25. That goes away. You got to remember, you'll have an a squared minus your b squared. A squared is x plus 5. Your b, which is 3, squared is 9. A squared minus b squared. Okay? That simplifies to be x minus 4. Cancel here. Plug in 4. You get root 9 plus 3, 6. Okay? Let's try this one. We got, no, do we have time? No, let's move on. We might go back to this one. Last technique is finding a common denominator. Used when you see fractions inside of fractions. So it says find the limit as x approaches negative 4 of 1/4 plus 1 over x divided by x plus 4. I can't plug in negative 4. I'll get 0 over 0. What I will do is try to combine stuff and get rid of maybe all these additions. To do that, I want to combine 1/4 and 1 over x. And we need a common denominator if we want to do that. So denominator is 4, denominator is x. Common denominator would be 4x. To make this 4x, I have to multiply by x. But of course, I would multiply the numerator by x as well so that we don't change what it is. We're multiplying by a version of 1. Over here, I would give this 4x by multiplying it by 4 over 4. That would change things into x plus 4 over 4x. And then, of course, you can go a step further and just say it's x plus 4 divided by 4x altogether. And now we still have this x plus 4 over here, down here. Now, what I like to do is whenever I have stuff, especially fractions being divided by more stuff, I like to say that like 3/4 divided by 8 That's the same as 3/4 times 1/8, right? Dividing is the same as multiplying by the reciprocal. So instead of making this a fraction within a fraction, I'll just say this is x plus 4 over 4x times 1 over x plus 4. And that might help me. Because what I can do with that is cancel right away, or if you want to just see the next step, you can have x plus 4 over 4x times the quantity x plus 4, combining my fractions. Those x plus 4's cancel, eliminating my problem, removing that whole, and I can find the limit as x approaches -4 of my new function. And that's -1/16. Okay. Why don't you guys try this one? I'll get you started if you're struggling. Here's where people make mistakes. We are subtracting the quantity of x plus 3. So when I subtract the quantity, that subtraction distributes. The 3's will go away, leaving me with -x over 3 times x plus 3. This 1 over x can get multiplied in if you want to, or it can stay out. Here the x's cancel. And then we just plug in 0 into this new function. So let me write that up. Now making sure we leave the -1. So that'd be -1/9. Okay. There's a challenge problem we might come back to. There's certain properties of limits. Now, I don't want you necessarily to write it down because I think it'd be a waste of paper. Because they're very obvious. If we wanted to take the limit of two functions added together, it's just equal to the limit of both of the functions separate from each other. This is almost intuitive, so it just obeys all rules that you would think would occur. If I have a constant being multiplied by a function and I want to find the limit of it, well, we could pull out the constant and just multiply it by the limit of the function we know. Now this is a good one. if we're trying to find the limit as x approaches a of x, what do you think that is? The limit as x approaches a of the function x. Any guesses? Sorry. Well, x is not a horizontal line. X is one of those diagonal lines, right? So at 1, I go to 1. At 2, I go to 2. So it's not just x, it's just what, Mr. Reynolds? A. A. You plug in A for x. Piece of cake. What about the limit as x approaches a of 5? Mr. Brewer? 5 is correct. X looks like this. If I plug in A, I'm going to get out A. 5 looks like this. If I plug in A, I'm going to get 5. Okay? So there's a bunch of examples that we could do, and you're going to have a couple on the homework. They're super simple. This limit as x approaches c of f is 4. If this limit as x approaches c of f is negative 1, and I say find the limit as x approaches c of 5g minus f, all you need to do is say, okay, 5 times the limit of g, negative 1, minus the limit as x approaches c of f, that's 4, that's negative 9. Done. So does that make sense? Yeah, you're just kind of plugging in the values that the limits are equal to. All right, good. So don't be freaked out on your homework when you see these problems. They're really easy. All right. If you want to do this challenge problem, go ahead and do it. But we have a minute left, so you're probably not going to get to finish it. But if you have time, if you got lunch, or if you're going off campus, I'll be here. I'll do the problem with you if you want to. This one's the funny.